Alright, so in this lesson we're going to talk about the structure of the atom, basically a little history on how we got to the structure we understand today. There's going to be a lot of technical stuff, and it's okay if we don't understand everything involved, but my goal is really that we sort of understand the science a little bit that led us to the current structure of the atom that we were talking about in the last class. I remember we started with Dalton, who basically had a very simplified idea of the atom, and we want to move beyond that, closer to where we understand the atom is today. So we're going to talk about some of the parts of the atoms, the protons, neutrons, and electrons. So remember from chapter 1, and by the way, if you're following along in Nearpod, we're on slide 11, 12 at this point. But back in chapter 1, an atom, remember, is the smallest particle of an element that has the same chemical properties of the element. So it still retains those properties. And we're going to learn about how the nucleus was discovered. The nucleus is a very small region at the center of the atom. And inside the nucleus, we've got protons and neutrons. Protons are positive and neutrons are neutral. Every atom has to have at least one proton, but neutrons, a couple of the smaller atoms can get away without even having any neutrons. But every atom has to have at least a proton. Then there's the third subatomic particle, the electron. So the protons and neutrons are really tightly packed inside the nucleus. But the electron's a little more, we're unsure about where it is. It's so high energy, it kind of floats around. Float is a bad word, but it exists around the outside of the atom. We call it the electron cloud. It's sort of an area where we expect the electron to be, but we're never really able to pin down its exact location outside the atom. So all three of these things together, the protons, the neutrons, and the electrons, are subatomic particles. Just remember, the protons and neutrons are inside the nucleus, and the electrons are on the outside of the atom. So there's a lot of information in this chart, so I'm going to go through it and do the best I can in terms of relaying all of this to you. So we've got, like I said, the electron, the proton, and neutron. A lot of times in nuclear equations, we might abbreviate those with their letter. So you might see them abbreviated as E, P, or N, lowercase. You see that over here too, but you might wonder why the proton has an H. So if we take a hydrogen atom is made up of one proton, and we find a hydrogen atom that doesn't have a neutron or an electron, it basically ends up just being a proton, because that's all that's left in the nucleus. So that's what that H stands for. It's a simplified hydrogen atom. Is essentially the same thing as a proton. But a neutron has no charge. It's neutral. That's the name neutron. Protons have a positive charge. And notice it's the same charge as an electron, except the electron's a negative. So in terms of charge, protons and electrons, let me be careful there. Protons and electrons will cancel each other out. Neutrons are always neutral. Now, we look at the mass. It would be very annoying to have to use scientific notation all the time to describe the mass of subatomic particles. So an electron, well, let's talk about the proton and neutron first. Proton weighs 1.67 times 10 to the negative 27. Neutron is similar. It's still 1.67 times 10 to the negative 27. It's a little higher in the fourth digit there. Now, because we don't want to always refer to those crazy numbers, they made a convenient unit called the atomic mass unit. and it is 1.66 times 10 to the negative 27th kilogram. What they did to determine that, we know a carbon-12 atom has 12 protons and neutrons in the nucleus. So they took a carbon-12 atom and divided it into 12 equal masses, and that is what we call the atomic mass unit. You might be wondering why it's less than the mass of a proton or a neutron. That gets into energy and mass relationships that I don't want to go into right now in detail, but essentially when the protons and neutrons combine in the nucleus, they lose energy, and in a sense, because they're so small, they're also losing mass when they do that. Einstein showed that energy and mass are essentially the same thing, and it shows much more dramatically when things are that small. But anyway, that's another rabbit trail we'll get to later on. Relative mass, though, if you look at how they compare to one another, proton and neutron are very close to one another. But the electron is very small. It's 1,800 times smaller than the proton or the neutron. So in terms of mass, it doesn't really make a difference. We can essentially call it zero whenever I add the electron in. I don't count it because it doesn't really do much in terms of sig figs. It doesn't really do much to add or subtract from the weight of the atom. So any questions on that? That's a lot of information thrown at you at once, but hopefully we see, and then we go back to the symbols. You can see the electron has 0 mass, but -1 charge. Proton and neutron both have 1 up here at the mass, but the charge of the proton is +1, charge of the neutron 0. And for these symbols, we put the charge up in the top right. These ones are more nuclear symbols. These ones are more, we'll see, like in chemistry, chemical equations. So hopefully we get this one. Which subatomic particle has a charge of +1? Yeah, the proton. We were paying attention there. And then which one has the least mass? I heard it. The electron. Good. So how do we know about the electron? Because Dalton certainly didn't know about the electron. We have this thing called a cathode ray tube. And I've got one here I can turn on so you can see. But I'm also going to show a video so those of us watching online can see what's going on here. But experiments did show that everything that I put in one of these cathode ray tubes, if I put a negative charge on one side and a positive charge on the other side, and I take everything out with a vacuum pump, somehow there's still something flowing through it. And you can see it as I showed in the video here. Got a lot of videos.
Okay, this is a cathode ray tube. What it essentially is, it's a vacuum chamber. There are no gases inside this glass tube. The only thing we have are 2 electrodes. One's called the cathode, the other's called the anode, and a fluorescent screen in the background. It's coated with some type of fluorescent material. When I turn the power supply on, we'll see a beam that causes that fluorescent screen to glow. Looks like a nice straight line, doesn't it? We call that a cathode ray because it emanates or begins at the cathode and shoots across over to the anode. J.J. Thomson was working with cathode rays. He really didn't understand what they were. I mean, we have electricity going in one side and coming out the other, but there's nothing inside to conduct it. It's a vacuum tube. So he decided to apply a magnetic field to this cathode ray, and he found something interesting. We apply one pole of the magnet to this beam, and we'll see what it does, and then we'll flip it around and see what the other pole does. This is my favorite part. Can you see what's happening to that beam? What does appear as though it's happening to it? moving, it's being repelled, isn't it, by the magnet. And flip the magnet around, and what do you think is going to happen this time? Well, if it's being attracted on one pole, see what's being attracted there? Let me rotate it so the kids on this side of the room can see it. See what's being attracted there? And then the other pole, you see what's being pushed down? What does that tell me about that beam? It has a what? It has a charge. Let me tell you about the poles of the magnet. The one that pushes it away is the negative pole. So what does that tell you about the charge of those particles? Negatively charged particles. And J.J. Thomson was actually able to do a charge to mass ratio of these particles, and he found that these particles were about 2,000 times lighter than a hydrogen atom. Now, at the time, that was very profound. What did Dalton say? Are there any particles smaller than an atom? J.J. Thomson just found something 2,000 times smaller than a hydrogen atom. Why is the hydrogen atom and something 2,000 times smaller than it so profound? Because hydrogen is the smallest atom, isn't it? So if we found something 2,000 times smaller, we have found our first subatomic particle.
So that's why that's so profound, because, at the time, they didn't really know what was going on with this tube. How can something flow through it if we evacuated everything out? We found out how small they were, 2,000 times smaller than the hydrogen atom. We knew that there had to be something smaller than the hydrogen atom. And they were actually called corpuscles at first, which I kind of like the electron better than a corpuscle. But we also knew that all matter had that in it. So that's who he was talking about in the video, Joseph John J.J. Thomson. He was able to use that experiment to measure the charge to mass ratio. Then we have another experiment, which is classic, Millikan's oil drop experiment. And this is how we got the charge of an electron.
In 1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrons.
So notice how he put a charge plate. I don't know if everyone catches this. He put a charge plate at the top that's positive and a charge plate at the bottom that's negative, put a voltage across it. So normally these oil drops would like to just fall due to gravity, but because there's that positive charge at the top, it's going to attract them back upwards against gravity. So some of them are going to slow down and some of them are even going to go back up.
Electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19th coulombs. He took this to be the charge on a single electron.
All right. So that's how they figured out the charge of an electron. And with those two pieces of information, they were then able to go and find the mass of an electron, which was 9.1 times 10 to the negative 31st kilograms. So at this point, we knew that there was something inside the atom that had a negative charge. But the problem is most matter is neutral. Most matter doesn't have a charge. So how they resolved this was they made something called the plum pudding model. And we kind of think as pudding in America as, you know, a liquidy kind of thing. You get it in a pudding cup. But in this time, in this place, pudding was more of like a dessert. It was more of a gelatinous kind of thing. So you have this kind of overarching pudding with a positive charge and then the negative electrons or corpuscles spread throughout. And I have another little video to show you with that.
So the word atom means uncuttable.
That's right.
So the Greeks were thinking of it as a tiny hard sphere.
That's right.
And even up into the 1800s, that was the idea of an atom. The smallest piece of matter, tiny hard sphere.
Yep.
But then we find out that that's not quite right.
Not quite. There were experiments in the 1800s that discovered the electron. J.J. Thomson's experiments really worked out that the electron was smaller than an atom, about 1,000 times smaller than the hydrogen atom.
And it was in all atoms.
That's right, not just hydrogen. Whatever material he did his experiments on, he found there were electrons in it.
There are electrons in all atoms. So I guess when you find something that's smaller than an atom, you need to propose a new model for the atom that actually has something smaller in it, some substructure.
That's right, so something like this.
This is our model of the atom.
This is our model of that. In his day, it was known as the plum pudding model, but here we have
Cherry tart.
cherry tart. Okay, but the idea being that we have an overall atom, usually pictured as spherical rather than 2D, but embedded within it, this is the important part, there are negative electrons represented by cherries, and they can come out. The overall atom is neutral, so that means the pudding part must be positive.
Now, how would you get one of these electrons out of our pudding here?
So electrons are negatively charged, so we'll need to put something very positive, which attracts electrons at a high voltage.
And that would have the effect of, say, like, plucking a cherry out of the pudding.
That's pretty much it. Yep, you could do it kind of like that.
So we're simulating what it would be like to put a positive charge up here.
That's right.
Pulling the electrons out of the atom. Wow.
That's quite a...
Delicious.
Yeah.
Well, that sounds delicious model of the atom, I've got to say.
Yeah. So shall we split the atom?
Why don't you go ahead?
You want me to do it?
Yes.
Okay. All right.
I know what's going to happen. A whole bunch of energy could be released.
Yeah, that's right. Ready? 1, 2, 3.
So that was just to give you an idea of what we mean when we say plum pudding model. But that didn't last very long because they were trying to show that this was the case, and they figured if we take some positive particles and basically shoot them towards some of these atoms, because there's that weak positive charge throughout the atom, we should see the positive charges get deflected a little bit, but they should pretty much just go straight through. Maybe we'll see what angle they go off course. But then that's where this gold foil experiment kind of changed everything. I think it's like one of the most important experiments in chemistry because it really gives us our understanding of the atomic nucleus. But they found that the alpha particles, the positive particles they shot at the atom, went off at very high angles, so they were being really deflected a lot. And some of them even came right back at the source that they were shooting them from. So we'll watch a video with that too. But to show you how surprised they were that this happened, I think the quote goes that Rutherford was saying, it's like if you were to shoot a cannonball at a piece of tissue paper, it'd be like if the cannonball bounced straight back at you. You wouldn't expect that. You might expect the tissue paper to slow it down ever so slightly, but they were seeing these alpha particles bounce off at very high angles, and sometimes they even bounce back. So we'll watch one more video here, videoing you out today.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil.
Most of the alpha particles pass through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
So let's go back to that for just a
Jangle.
sec. Whoops. So yeah, you can see how most of them went straight through, but the ones that hit the nucleus, this thing's so densely packed with positive charge that it really bounced it at high angles off. And this picture doesn't even do it justice how small the nucleus of an atom is. In fact, most of the atom is empty space. If we compare it to PNC Park or any baseball stadium, the atom would represent the overall stadium, and the nucleus is so small that it would be second base. So this little tiny dot you can't even see would be second base. That's how packed the nucleus is in relation to the rest of the atom. And then everything outside here is empty space with the electrons kind of bordering the outside of the stadium. So really, really tiny compared to the rest of the atom is that nucleus, which is kind of crazy to think that most of matter, when you break it down, is just empty space. But that's what he did call that. They remodeled the atom, and now we have a nucleus in the center. We still don't know a lot about the electrons. We're going to come up with some ideas for the electrons later, but there's just a picture of what was happening, and you see how the deflections happen. You had these really wide deflections where the nucleus was. So that experiment established that most of the atom is empty space. So let's just talk a little bit about the subatomic particles. Every atomic nucleus has protons and neutrons, except for sometimes the hydrogen atom, like we said, does not have neutrons. A proton has the same charge as an electron. They're equal in magnitude. And because atoms have the same amount of protons, or the same number of protons and electrons, they are electrically neutral. And on top of that, the neutrons don't add any charge because they're neutral as well. So just remember, protons and neutrons are inside the nucleus. Electrons are on the outside. So because different atoms of the same element can have different number of neutrons, the only thing that determines the identity would be the number of protons. So the amount of positive charge really determines the atomic identity, and we have a fancy name for that. We call it the atomic number, and that's how the periodic table was organized. One thing we have to note, though, we just spent all this time talking about how, opposites attract, positive and negative charges attract to each other. Well, it might not make sense how we jam all these protons really, really close to each other in the nucleus, because ordinarily protons with their electric force would want to repel each other, but there are these even stronger forces within the nucleus called nuclear forces that actually hold the protons, the neutrons, and to each other and to the other one. They hold all those different pairs together. And that's why they were joking about splitting the atom. When you split the atom, you have all sorts of energy released because these forces holding the protons in the nucleus are so strong. You can see how densely packed it is, that all that energy is then released. It takes a lot of energy to split the atom for that reason. And then on the size, and then we're going to wrap it up here, the radius of the atom would be the distance from the center of the nucleus to the outer portion of the electron cloud. And these radii are so small, we have to use a unit like the picometer, which is 10 to the negative 12th. The picometer is going to be representing the size of atoms. So that's it for section 2.